Okay, welcome to lecture 12.2. All right, now let me give some little thoughts about what happens when you try to get, if you try to get Stata to estimate this. So, by the way, Charles and I did this in SAS. It worked in SAS. Here is one problem, though, why Stata will choke when you do it. Uh, so, recall, I've rewritten this. So, wait, I think already, did I? Yeah, sorry, already deleted the probit likelihood function. But the probit likelihood function just looks like this times. Yeah, by the way, this is all to the yi. Okay. Now the probit likelihood function is just this times called 1 minus phi of that same stuff. Beta 0 plus beta 1, x1i plus beta 2, x2i plus beta 3, x3i, all to the 1 minus yi. Okay, so that is the probit likelihood function. Okay, now when you do have data like Charles and I did, where we set the dependent variable equal to 1 for every single observation. So when that's true, this yi is always 1. Okay, so do it. I'm just going to erase it. So that, because that's 1, so it's just that raised to the 1 power. So it's just that times this raised to the 1 minus yi. yi is always 1, so it's always raised to the 0th power. So this term is always 1. Okay, so that's what the likelihood function looks like when the dependent variable is always 1. Okay, and this is what Charles and I are trying to run. All right, here is the problem. There's a notion in Probit called exploding coefficients. And this happens whenever, if you have an independent variable that's binary, so it's 1 or 0, and that independent variable perfectly predicts the dependent variable. If that happens, the maximum likelihood estimate for the coefficient on that independent variable is always going to be infinity. And it always works to make that infinity. And we say that your coefficient explodes. And we have an example of this. So now Charles and I said, no constant, don't include the constant. Okay, I'm going to talk about that in a second. But suppose we hadn't done that. Suppose we had a probit where the dependent variable is always 1, and we do have a constant. Okay, and so here we would have a case of that. The constant is just multiplied by a vector of 1s. Okay, that's how we estimate the constant. Just create an independent variable of all 1s. And so that independent variable of all 1s perfectly predicts the dependent variable, which is all 1s. Okay, and you can see why the coefficient is going to explode. So notice that, here's we have the likelihood function. It will always increase when beta 0 increases. So it's completely monotonic, or always strictly increasing in this beta 0, this likelihood function. So no matter what you've chosen for beta 0, if you make beta 0 just a little bit bigger, this L will get bigger. And so what that means is if you want to maximize this likelihood function, you want to set beta 0 just equal to infinity. And that makes every one of these probability terms, big phi of infinity equals 1. So when the z-score is all the way out in the right tail, you get the probability is 1. So when beta 0 equals infinity, everything else is finite. You're going to have phi of infinity, which is 1, and there's no way to make the likelihood function any bigger. Okay, so once again, if this is your likelihood function, the maximum likelihood, the way to maximize this is to set beta 0 equals to infinity. So if you ran this, a probit where the dependent variable is always 1, you're going to get your constant term, this beta 0, is going to explode. It's going to become infinity. Okay, so Stata kind of understands this. The guy who wrote the program knew, like, wait, you can't have a case where the dependent variable is always 1, because if you do that, the constant's going to explode to infinity. So you get an error term if you run this. Okay. Now the problem is that Charles and I, we tell it no constant. So we say there is no constant term. There is no beta 0. So we're trying to tell Stata, no, trust us. You can estimate that because we told you no constant. Stata, it's a bug in my view, that Stata has not looked to see that, yeah, it is a problem if your dependent variable is always 1, but if at the same time you tell it no constant, then it isn't a problem. But Stata, as I speak in November 2021, as far as I'm aware, they haven't learned that bug yet. They haven't fixed it. Okay, so what that means is you can't do our technique, Charles and my technique in Stata. You've got to do something else. Okay. Now, that's not quite true, and here's a good thing to remember. My colleague Jeff Lewis from UCLA had a great expression. Says, Stata will do whatever you want it to do, but sometimes you have to trick it. Okay. So that's what I'm going to do next in the remainder of this part. I'm going to show how to trick Stata. All right. So the first trick I want you to notice is that, okay, if we have so we have a normally distributed random variable, okay, suppose it's centered at 0. So if that's z, okay, so that area here is phi of z. Okay. All right. Now, this area is 1 minus big phi of z. Right? Okay. Now, let me switch colors. Now, what if we, because the normal distribution is symmetric, if we looked at just negative z, and looked at this area, the blue area, is phi of negative z. Okay. If I drew these right, because this is symmetric, the area under of this shape is the same as the area of that shape. It's got to be the case if this normal distribution is symmetric. Okay. So what we have is, for normal distribution, for normal CDF, for all z, phi of negative z has got to equal 1 minus phi of z. Okay. So here is what we're going to do. So here's our likelihood function. Okay. L equals big phi of this stuff taken over where I equals 1 to 4. Okay. Consider the first, the very first term of these, where this I, the superscript I, is just 1. Okay. Or I don't know. Or let's make it 3. The third observation. Okay. What does that equal? It's just phi of beta 1 x1 to 3 plus beta 2 x2 to the 3 plus beta 3 x3 to the 3. All right. That's what it is. That's what the third term of this. So this is a product of 4 terms. The third one looks like this. Okay. Now, let's use this fact. Phi of negative z, for all z, phi of negative z equals 1 minus phi of positive z. Okay. So what that means is we can multiply everything inside the parentheses by negative z. Okay. Put a negative sign there, and then it equals the phi of that negative stuff. So here's what I'm going to do. Negative of that has to equal 1 minus phi of the original stuff. Beta 1, x1, 3, plus beta 2, x2, 3, plus beta 3, x3, 3. All right. Okay. What did I do? You know what? I should have done it the other way. Okay. Hope you can see through this arithmetic. We could have done it the other way. Instead, suppose that's positive. If I had made that positive, then all of that has to equal negative of that. Okay, another way of saying that is that just from that term, just subtract phi of negative z from both sides. It says phi of z must equal 1 minus phi of negative z. Okay, so that's what I've done here. So phi of this is z equals 1 minus phi of negative z. Okay, all right. So what that means is our third observation. So the third term in this big product of 4 terms looks just like this. If we replace that term with this, 1 minus phi of negative z, blah, 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 equals that, we can write that, we can rewrite that equals 1 minus phi of beta 1 times negative x1, 3 plus beta 2, x2, negative x2, 3 plus beta 3 times negative x3 of 3. Okay. All right. So that's what we've done. We take the original term, just take 1 minus that term, and then put a negative sign in front of all the x's. Okay. It's the exact same thing. We haven't changed the likelihood function. That third term is going to equal. It's going to be the same as it was before. Okay. So what that means is that we can take our original likelihood function this here, and we can take one observation. Oh, and by the way, notice that this is when this is all, okay, I erased all the yi's. Here we had yi equals 1 for every case. If instead we changed y3 to 0, before we had yi equals 1 for all the observations, for y3 we change it to 0, we get that other term, 1 minus that, okay? So if we do this, okay, we take the third observation, we change the dependent variable from 1 to 0, and at the same time multiply all the independent variables for that observation by negative 1, this is what we get. This is going to be the third term. Okay, if we do those two things, change the independent variable from 1 to 0, change all and multiply all the independent variables by negative 1 for that one observation, we get this. Okay, now I've just shown you that term equals exactly this, which is what we originally had. So if we do that transformation on the third observation, we haven't changed the likelihood function at all. Okay, but the good thing is that we've now tricked Stata. Now, Stata does not have the case where the dependent variable always equals 1. We have that one observation where it equals 0. And Stata will no longer choke now. It will say, okay, I will try to estimate it. And it will give you estimates, and it should give exactly the estimates that you would get from maximizing this likelihood function if you just do this little trick. So in this case, Jeff Lewis was right. Stata will do what you want if you trick it, okay? So that is that one little trick, okay? So that is my paper with Charles Stewart. I'm not going to go over the substance of it. So we get estimates. Let's see. I guess one final little thing. One final little problem. I told you about the exploding coefficient. Okay. And I showed you when the dependent variable is always 1 and you have a constant, you get an exploding coefficient. There's another case you can get that with our data. So these x's, they involved, it was always positive if a person transferred onto that committee. So if that, x3, if someone transferred onto committee 3, x3 is going to be positive. Transferred off of it, x3 is going to be negative. Okay. In this likelihood function, suppose there was some committee such that the x is always positive. So no one ever transferred off of that committee. All right. If that's true, say that x3 is always positive for every observation. For the same reasoning that we did just a minute ago, the maximum likelihood estimate of beta 3 is going to be infinity. Okay? No matter what beta 3 is, if you increase it a little, because that x3 is always positive, or it's always non-negative, say, then that will always increase the likelihood function. So the likelihood function keeps on increasing as long as you increase beta 3. It doesn't stop. That's always true until you get to beta 3 equal to infinity. So if you ever have any committee that no one ever transferred off of, and we had one of those committees, I think it was Ways and Means. I think that was the case. So that was, the most popular committee in our data set. If anyone got on Ways and Means, they never left it. So what that meant is that the beta for Ways and Means exploded. And we just did that. We said, well, let's omit all the Ways and Means observations. We put in the table that our estimate of that for it was infinity. And a similar thing happens if there's some committee that no one transfers off of, or excuse me, no one transfers onto. So something like post office was in danger of being that way. So if they're ever in the data set, they always it's always the case that they almost always leave it. They never transfer onto it. If that's the case, say post office is committee 2, then that the maximum likelihood estimate of beta 2 is going to be negative infinity. So you have a coefficient that explodes in the negative direction. Okay, so that's another aspect that can happen with Probit, and because we use Probit to estimate our likelihood function, it affects our likelihood function the same way. Okay, you can have exploding coefficients. Okay, so I'll end there. Again, if you're interested in the substance, I encourage you to look at the paper. We give estimates of the V's. Let's say which committee is more popular than others, and that's our main conclusion. Okay, that's part 2. Next, I'm going to talk about the Levitt paper, how senators vote, and that will be in 12.3. Okay, see you there.